Is it from you? Can you help me out here a little bit? I don't know. I got technical difficulties.
This is CS50 at Miami Dade College. Thanks to an invitation from our friends here at the college and at Launch Code, we are thrilled, in fact, to be here. So I'm joined here today with Colton Ogden, with Scully, with Shelly, with Davin, Ramon, and back, and our kind hosts. And so what we thought we'd do tonight is do it as we do it in Cambridge and actually do the lecture live for the next hour or so. Then we'll pause, we'll do a bit of discussion, interactive Q&A, and then mingle at the end and hopefully get a few questions from you guys on camera and interview you about what your experiences have been like thus far and where you hope to take things. So please interject at any point with questions, but let me begin with a look at a job I once had. It was during graduate school. One of my favorite jobs was working for the Middlesex County District Attorney's Office, so essentially the local prosecutor's office doing digital forensics. And I didn't know all that much about this world, but in grad school I was definitely interested in forensics, like recovering information that had been corrupted or that had been deleted intentionally or unintentionally. And so I had this amazing opportunity to work alongside of an actual forensic investigator, taking in as input hard drives and floppy disks and, curiously, sometimes like monitors and keyboards and mice from the police who would drop them off in the investigation of some crime. And then my mentor and I would be charged with trying to find evidence on that hard drive or floppy disk or the like. Now, sometimes the criminals in at least Middlesex County weren't all that savvy, and so it was pretty much as simple as double-clicking on my documents and voila, case closed. Other times there wasn't any data whatsoever there, but yet other times there was an opportunity to try to figure out what zeros and ones were still on the hard drive, even though he or she had tried to cover their tracks intentionally or unintentionally. Now, unfortunately, in the media, movies and film and TV, there's sort of this ongoing narrative where if you have imperfect information, no big deal, just ask the techie to say, to enhance it for you. Can you zoom in on that? Can you see the glint of the criminal in their eye or some such thing? So we brought a few such clips to set the stage for what ultimately is going to be one of your next problem sets after Breakout, that world of forensics and recovering information that may or may not actually still be there. So allow me to dim the lights and take a look at some of our favorite clips from movies and TV shows that you may indeed remember yourselves.
Hold it. Run that back.
Wait a minute. Go right.
There, freeze that.
Full screen.
Okay, freeze that.
Tighten up on that way.
Vector in on that guy by the back wheel.
Zoom in right here on this spot.
With the right equipment, the image could be enlarged and sharpened.
What's that?
It's an enhancement program.
Can you clear that up any?
I don't know. Let's enhance it.
Enhance section A6.
I enhanced the detail, and
I think there's enough to enhance. Release it to my screen.
Enhance the reflection in her eye.
Let's run this through video enhancement.
Edgar, can you enhance this?
Hang on. I've been working on this reflection.
Someone's reflection.
Reflection.
There's a reflection of the man's face.
The reflection.
There's a reflection.
Zoom in on the mirror.
You can see a reflection.
can you enhance the image from here?
Can you enhance him right here?
Can you enhance it?
Can you enhance it?
Can we enhance this?
Can you enhance it?
Hold on a second, I'll enhance.
Zoom in on the door.
Times 10.
Zoom. Move in.
More.
Wait, stop.
Stop.
Pause it.
Rotate us 75 degrees around the vertical, please.
Stop. And go back to the part about the door again.
Got an image enhancer that can bitmap?
Maybe we can use the Pradeep Sen method to see into the windows.
This software is state of the art.
The eigenvalue is off. With the right combination of algorithms.
He's taken illumination algorithms to the next level, and I can use them to enhance this photograph.
Lock on and enlarge the z-axis.
Enhance.
Enhanced.
Enhance.
Freeze and enhance.
To enhance an image? Your answer should almost always be no. You cannot, in fact, enhance what is not there. Indeed, by the end of the CS50, you should have an underlying appreciation for certainly how information is represented. And if information per week 0 is represented with zeros and ones, bits, there's only a finite number of those. And so if you can't see at first glance, typically, the glint of the criminal in someone's eye, simply zooming in and enhancing isn't going to give you information that isn't already there. For instance, some of you may know from earlier weeks in CS50, CS50's own Davin Farnham, who manages the course. Now, suppose we're a little suspicious by that glint in his eye, and we try to zoom in. Well, if I do indeed zoom, and just to draw awkward attention to him, there is Davin in the very back of the room. You'll meet him in just a moment. If we do try to enhance Davin, this is what he starts to look like. And if we try to enhance further on his eye in the top right-hand corner there, that is the extent of the reflection you might actually see. Now, this is all to say that in the next problem set, you'll actually deal with the art of forensics and actually trying to recover information that may or may not be there, and more fundamentally, dealing with something called file I/O. And I/O is kind of a buzzword in CS. What does I/O stand for? Yeah, so just input and output. And so file I/O just literally refers to the process of saving files and reading files, and maybe editing them, maybe deleting them, but generally providing input and output in the form of files. Now, sometimes those files are text, like text source code that you guys have been writing in C. Sometimes it's binary, and indeed, in the world of binary, we have all sorts of file formats, Excel files, Microsoft Word files, but also, of course, things like JPEGs, which, of course, are most commonly used for what context, what use case? Yeah, so images, photos we take with our cameras or phones these days are very often stored as JPEGs. But what's interesting, and what you'll really get your hands dirty with in the next problem set, is that what's interesting about JPEGs and file formats more generally is that a file format, at the end of the day, is just some pattern of zeros and ones. And people, companies often, have decided, somewhat arbitrarily, that certain patterns of zeros and ones are going to uniquely identify their files. So Microsoft has essentially decreed that if you see a certain pattern of zeros and ones in a file, that means it's a Word document. If it's a different pattern, it's an Excel file. Or maybe it's something like a JPEG or the like. And in fact, what's cool about JPEGs is that even though there's some pretty fancy math underlying the compression of a JPEG to use fewer bits to store a reasonable approximation of the photo that you took with your camera, every JPEG in the world starts with 3 bytes specifically. So if you look at the first, the second, and the third byte inside of a file that you yourselves have taken with a camera, they start with the number 255, 216, and 255. Why? Sort of for historical reasons, but that's invariant. And so what is this implication? Well, if some bad guy has a whole bunch of JPEGs on his or her hard drive and they've been deleted intentionally or unintentionally, or maybe it's just you who accidentally corrupted a compact flash card in your camera or some kind of memory stick, and you can't access the data in the usual way, well, what if you could write a program, maybe in C, that iterates, so loops over all of the zeros and ones in your hard drive and just looks for these patterns? Do I see 255, 216, 255? If so, at least with high probability, that probably demarcates the start of a JPEG. Could just be random chance, but with pretty high probability, that means here comes a JPEG on your hard drive. And so indeed, in the forensics problem set, what you'll do is exactly that. We've gone around campus a few months back taking pictures of CS50's teaching staff. In reality, we kind of cut a corner this year and we just trolled their Facebook pages to find semi-embarrassing photos, but we then put those on the equivalent of a memory stick and then accidentally corrupted it or erased it. But it turns out that when you erase data, and certainly when you corrupt data, you haven't necessarily lost all of it. Maybe you've lost a little bit of it such that it's no longer obviously JPEGs or photographs, but there's enough of those zeros and ones still there that a smart person can write code to actually recover those zeros and ones and realize, ooh, this is probably a JPEG. Ooh, this is probably another JPEG. And you'll do exactly that. We'll give you a so-called forensic image of a compact flash card or a memory stick from some camera, and you'll have to write C code that iterates over those zeros and ones and finds a whole bunch of unsuspecting CS50 teaching fellows from back home. Now let's make this a little more technical for just a moment. Recall, of course, from forever using the decimal system in life. So 0 through 9 is, of course, what we humans use. Computers obviously use binary, typically. At least at the end of the day, they're dealing in zeros and ones, which is fundamentally the same thing. It's just a different base system per week 0. But it turns out that we can think of today in a different base system altogether. And if you think back on the very first P set, 0, we asked you to kind of noodle through hexadecimal, which means you don't have 2, you don't have 10, you have 16 digits at your disposal, 0 through 9, and then, spoiler, A through F to get you from 10 all the way up to 15. And so indeed, just in the world of file I/O, this is not a requirement, but it's just convention to typically talk about data in terms of hexadecimal. Why? Because it kind of represents itself nice and cleanly. So here's the alphabet for hexadecimal, 0 through F. But if we want to now take this pattern of bits that represent the start of a JPEG, consider how we might represent this. So I'm going to claim, and if you'll forgive an assumption from week 0, that this is super fast to do. At least 255, probably pretty easy to do. You might have to think about 216. But indeed, let me stipulate that those patterns of zeros and ones represent respectively 255, 216, and 255. Now let me just add, for human's sake, a bit of white space. Let me spread out some of those bits so that they look like this instead of this. So I'm just adding some white space, but deliberately chunking them instead of in terms of 8-bit bytes, just 4-bit chunks. Because what's nice about hexadecimal is because it goes from 0 to 15 for 16 possible values, if you consider that 4 bits also gives you a possibility of 16 values, you can start to think of chunks of 4 bits as just a hexadecimal character. Maybe it's 0, maybe it's 15, but you need 4 and only 4 bits to represent a hexadecimal character because it's 16 total values. So this is only to say that we can start to throw some hexadecimal notation at this. And this is only to say further that generally when a computer scientist or a programmer is just representing data, it's not that useful to talk in terms of decimal. That's a human thing. It's certainly not helpful to talk about it in terms of binary. That's way too low level to be compelling. So we computer scientists typically use hexadecimal and would just write the first 3 bytes of a JPEG as OXFF. OXD8, OXFF, where the OX is just a human convention. Means nothing other than here comes a hexadecimal value. And then FF. Let's tease this apart for just one moment. Why is FF 255? Well, if you kind of explode it in your mind, what's an individual F represent? Not 16 quite. 15 is the highest because we start counting from 0. So 15. But 15 in binary, just to rewind, is what? 1111. And so FF is like 1111, 1111. And so FF happens to represent 255 when you think of those 2 chunks of 4 bits as like this collective 8. So this is just kind of mental gymnastics. It hasn't really gotten us anywhere fundamentally smarter other than to just introduce just what's a convention. Because indeed, in the problem set involving forensics, it'd be very tedious to talk with you in terms of 0s and 1s. It's not all that normal to use decimal in the world of computers. So you'll find in the P set and in life in general with dealing with files, people just tend to speak hexadecimal. But it's just a convention. There's nothing sort of fundamentally interesting about it. But there are other file formats besides JPEGs. And the forensics P set is also going to give you an image that if you think back to childhood perhaps, you might have like, if you ate cereal like I did as a kid or whatever brand this was, you sometimes got these like secret images inside of a cereal box that had a lot of red speckles, a lot of red noise. And the way to see the image was to get some like piece of red plastic, hold it up over the cereal box, and then voila, there was some secret message like buy Cheerios or something silly like that. But we'll give you such an image and challenge you to iterate over those pixels, those dots on the screen, and do some kind of manipulation to recreate the sort of physical idea of this red piece of plastic. So we'll give you essentially a secret message, and you'll have to figure out what it is by creating digitally the notion of that red piece of plastic. But at the end of the day, you're just manipulating things that you'll find are just called RGB triples. It's kind of dated these days, but back in the day, RGB was all the rage. RGB stands for? Yeah, red, green, blue. And what's nice about that convention is that by using a bit of red, a bit of green, a bit of blue, you can represent essentially any color that you want. And so this is nice because using these fundamental building blocks, you can create images using those 3 colors. And so you might recall this from yesteryear. Some of your computers might still have this as a wallpaper on it, which Microsoft popularized. This is, in fact, a BMP, a bitmap image. And a bitmap is just referring to the fact that every sort of pixel is represented with some bits underneath the hood. Now, just as a fun fact, or rather, we'll get to the fun fact in just a moment, this is deliberately meant to overwhelm at first glance. But this is a data structure, so to speak, that represents what's underneath the hood of a bitmap file. And I say it's meant to overwhelm because the problem set on forensics, we'll walk you through this very deliberately. But for now, I just wanted to wave my hand at a few details. Namely, there's a whole bunch of bits at the top of a bitmap file. There's a whole bunch more bits, and we'll call this metadata. It's just like 0s and 1s that have to be there that indicate sort of ancillary information like how big is the image, how wide is the image, how tall is the image. So useful, but not really fundamental to like seeing the image. Seeing the image requires knowing those patterns of red, green, and blue because there's so many thousands or millions of these little dots that are colorized that create an image like the Windows wallpaper. And so you'll see in this problem set on forensics this notion of an RGB triple. So red, green, blue, triple, red, green, blue, triple, and so forth, which just means what color is this dot? What color is this dot? What color is this dot? And then repeat for every row in the file. And so you'll find that a bitmap file, even though at first glance this seems a bit arcane, it's actually relatively straightforward. The people who invented it, and this is drawn from some Microsoft documentation, simply decided that we'll represent this pixel with a 24-bit value. 8 bits for red, 8 bits for blue, 8 bits for green, and then we're going to do the same thing again and again for every dot in the image. But unfortunately, in C at least, we don't yet have a way of representing an RGB triple, right? To date, all we know how to represent is ints and chars, strings, but we don't have like triples or colors. So we're going to need sort of a vocabulary with which to express these. We'll do that today briefly by way of something called a struct. It turns out that C, the programming language, allows you to create your own custom types that humans years ago didn't anticipate we would want. So for instance, it's pretty reasonable to expect that the people who invented C certainly wouldn't have decided unilaterally what a student is, tens of years ago. But we, as humans now, could certainly imagine describing a student in terms of his or her name and his or her house, as we say in Cambridge, or dormitory. So we might describe a student in terms of those values. And what other types of data is associated with a typical student in like a university system? Student ID number is a good one. Phone number, maybe an email address. So there's a lot of data. But what we can do now with this technique called a struct or structure in C is we can create our own types that represent real-world data that we want to represent in a program. And that's what we'll do here right now. I'm going to go ahead and scroll over to my CS50 appliance. So I have a gedit window here, and I'll zoom in as needed so that folks can see in back. And I'm going to propose that we implement a program that quite simply reads in a student's name and their dorm, and then ultimately gives us the ability to store values in those fields. So let me go ahead and do this. I'm going to go ahead and include standardio.h. I'm going to go ahead and include CS50.h. down here, and let me start to zoom in. I'm going to go ahead and do int main void. And now in here, you know what? I want this program to support at least 3 students. And at least from a few weeks back, you may recall that we preached that you shouldn't just hard code numbers like 3 in your program. Minimally, you should use what instead? A variable, but more specifically, if you want to hard code it nonetheless, it wouldn't be a variable which varies, but a constant. Right, so we can do this in C. And let me scroll back up and just do like sharp define. I'm going to call this students. And all caps is just a convention so that it's glaringly obvious this is a constant by convention. And I'm just going to say 3. And I'm just anticipating wanting to make a program that involves somehow 3 students for the sake of this discussion. And now down here, I might want to do something like this. Well, a name. What's the right data type for a student's name in C? So string, right? It's a series of characters. So string. But I could do, OK, name 1 for the first student. I could do name 2 for the second student. OK, good, good. Rubs you the wrong way. What's the obviously better approach? OK, so use an array. So let me change the semantics a bit. Names, and then 3 names. Students, right? So let's not regress there. So students. So this is pretty good. We already know that an array is sort of your go-to data structure when you want a whole bunch of the same data type. OK, but now let's see where this leads us. For a dorm, aka house, that too I'm going to claim is going to be something like a string. So I'm going to say like houses, and this too should be students. And this seems pretty good so far. And now just for the sake of discussion, let me go down further here. Let me go ahead now and zoom in a little bit lower and do for int I gets 0, I is less than students, I++. So I just want a loop that's going to iterate 3 times. So some hopefully familiar syntax at this point. And now I want to do something like printf name. And then I'll do something like names bracket I gets, and how do I prompt the user for a string at this point? Yeah, so getString in the CS50 library. And now I could do something like printf house, just to tell the human what I'm expecting. And then I could do houses bracket I gets getString. So this is pretty good so far. But now suppose that ID number, that was a good one. I like that. What data type might be appropriate for an ID number? Yeah, integer. Yeah, and maybe there are a certain format, but int is a reasonable starting point for a typical ID. So let's do an int, maybe IDs bracket students. And now if I want to go in here, you could imagine me doing something like prompting the user for their ID. And obviously, this needs to change to get int. Yeah, and then let's change this to IDs. But here, too, is sort of a new pet peeve that should start to rub you the wrong way. This is kind of devolving already into just copy and paste. Moreover, and a little more sort of disappointingly, it's just convention at this point in the story that names bracket 0 and houses bracket 0 and IDs bracket 0 is presumably all going to refer to the same students. but that's kind of an assumption we, the programmer, are making. And similarly, names bracket 1, houses bracket 1, IDs bracket 1 refers to another student. But if you can think of it in your mind, this is kind of like mentally maintaining just sort of arbitrary association among all of these arrays. Wouldn't it be nice if we could just kind of lump all of this related data together? And indeed, we can. If I scroll back to what we had on the screen earlier, via this syntax here, can I tell C, or can I tell Clang, the compiler, bring to life a new data type that's not int, that's not string, that's not char, not float, double, whatever, that is called literally student. And think of this now as a black box. The keyword here would be encapsulation in computer science or programming, that encapsulates other data members that are of known primitive, very familiar types, like a string or two strings and maybe an ID as an int. So let's go ahead and do this. Let me go ahead and open up a separate file that I made in advance. And as always, all this code is available online. This file is called structs.h. And notice that there's a bunch of comments at the top. That's not all that interesting. Here is an include. And just as a little teaser, how come I am including CS50.h? Yeah, I want to use the keyword string. And today, we're going to peel back that layer remarkably to see that string is actually just a CS50 simplification, a training wheel that's about to start coming off. And then down here is literally copied and pasted from what I put on the screen a moment ago. And if I wanted to refine this further, I could say int ID, semicolon. And what's nice now is that if a student is indeed characterized by a name, a house, an ID, and maybe some other stuff, now that is truly encapsulated inside of a keyword, student, that has sort of fundamental meaning that I can now toss around as though it were an int or a string or a char. It's an actual data type that I've taught C to understand. So if I now sort of pull a pre-baked cake out of the oven, so to speak, this is a file called structs0.c that I wrote in advance that's available online, that now includes a whole bunch of files, but most of these are familiar. String.h is something we might use occasionally too. But notice this syntax. Because I've deliberately, and this is not a requirement, I just kind of anticipated maybe it'd be nice to put student struct in a separate file so that I can use it in the future in other programs. I factored it out into a header file. And what's this highlighted line then telling Clang to do effectively when it reaches line 14? Yeah. Exactly. Load the file, include the file, essentially open it up, copy and paste its contents right there so that the file can be shared across multiple programs. Now down below, I'd seem to have done the same thing. I defined a constant, and I also put some comments in the file for reading through later. And now notice how clean the declaration of an array of 3 or more students is. I literally can use these very straightforward semantics of give me an array called students, each of whose member is of type student. Singular, and the fact, I mean, frankly, it's arguably a bit misleading that I'm using student in 3 different sort of forms here, capitalized or with an S, but each of them means something slightly different, and this gives me an array of 3 student structures. But we need a new piece of syntax that's super easy to use that lets us dive into a student and access his or her ID or name or house, and that syntax is going to be as simple as this. Here's that same loop from before, but this time fleshed out to actually get a name and a house iteratively into the same student structure. So notice what I have here is students, which is the array, bracket I. So give me the ith student, and store in it whatever getString returns, which is old hat. And then same thing here for house. So we still need the loop, and we still need to identify the name and the house with individual lines of code, and we'd have to do the same for an ID. But now we're sort of tucking inside of this little black box, so to speak, the name, the house, maybe the ID, the phone number, the email address, and anything else so that it sort of stands on its own and lives on its own in memory. And we don't need this sort of arbitrary assumption that we have all of these arrays that just happen to refer to an array of students. We can actually give ourselves an array of students. Any questions on that element? Yeah? Where do you save the structure? So you declare the structure wherever you want, either in your C file or in the .h file. And I happen to put it in the latter, in the .h file, so that I could use it in other programs. And what C effectively does, C is a very simple language. So when I have declared a struct called student, and let me revert back to the original, as we'll see today, a string in C, at least as we've defined it, is 32 bits. So what's really happening underneath the hood is that when I declare a variable or a structure called student, I can think of it, as I was saying, as a sort of black box like this. but half of that black box can be thought of as a name field. Half of that black box can be thought of as a house field, each of which can store a string like David, and back home I used to live in a dorm called Mather House. And what the computer is doing is effectively, and this is a little white lie until later today, what the computer is doing is just putting the name in memory, in RAM, followed immediately by the house. In theory, they're back to back. And this is nice because it actually aligns nicely with my sort of hint earlier that this thing, which looks crazy more complicated than a student, is deliberately written out on the screen line by line by line, because indeed when you have a file on disk that is a bitmap in this case, each of its bytes are back to back to back to back to back, and in memory too, once that file is loaded into RAM, it's going to be loaded into something like this, but called a BMP struct, not a student struct. So you're just sort of treating chunks of memory virtually as though they are some new data type fundamentally. But at the end of the day, super fundamental data types still. Strings, ints, chars, floats, doubles, and the like. Good question. Other questions? Yeah? When I saved the file with the student definition, declaration, it can depend. You can either put it in a C file, or you can factor it out, as we've been starting to preach, to clean up your code into a .h file. The motivation for putting something like the student declaration in a .h file, just to be clear, is what? What's the arguable utility of doing that? So you can use it in another program. So I don't have to resort every week I write a program involving students to just copying and pasting some code I wrote before. I've just factored it out. But I could also just literally put it at the top of my C file. Specifically, if I go back into the appliance here, if I go temporarily and copy the structure from the H file, I could go into struct0.c, and at the very top of my file, get rid of this, include, and just put it right there. But very quickly, your world can devolve into a bit something messy by too much copying and pasting. Yep? Yes, it's not quite a library. A library more like properly would be code you've already pre-compiled, but it's very similar in spirit. A header file is just source code. A library is binary code, zeros and ones. Other questions? Does the header file have to be in the same folder? In this case, yes, but it wouldn't have to be. If I undo the change I just made, suppose it were in a folder called foo, I can do foo/structs, or I can use other notation still. But if I don't specify, yes, that's assumed. Yeah?
The name and the house.
Mm-hmm. Good question. Where is the 0 \? In fact, and this is where I'm sort of giving a little white lie here, it is somewhere here, but frankly, it's the \0 you're referring to is actually something over here. And in fact, just as a teaser, I don't want to go here just yet. There are more characters, and in fact, if I did write David, it's probably DAVID \0 over here. And what we're about to start seeing today is that there's something called a pointer that's pointing from these 32 bits over here. But getting slightly ahead of ourselves, but that's where we're going with this. So the \0 still comes into play. So in fact, that's actually a perfect segue to where you and we left off virtually on Tuesday. But first, I thought I'd share with you the before and after. So this, of course, is what the Windows XP backdrop looked like for quite some time. In reality, so that's a photo of it more presently that you can find on Wikipedia and elsewhere. So recall that we talked about this notion of swapping on Tuesday. We had Laura in Cambridge do this, but is there a volunteer in the room, comfy appearing on camera, coming on? This was the first hand I saw. Yeah? Come on up. What is your name? Maria, David, nice to meet you. Come on up. OK, so we went to 7-Eleven right before class and paid for 3 empty cups, as they seem to charge. So let's go here. And I also brought some orange juice and milk, neither of which we should drink because it's been like 4 hours. And what we did recall when talking about swapping is if we have a variable like x, we might store some value in this, like this white milk here. And then if we had another variable y, we could store this orange juice over here. Okay, safety seal. But now, of course, if the goal for Maria is to swap these two values, how would you go about doing that? And before you do it, sort of walk us through your reasoning.
Well, I would first swap the orange in the middle.
You put the orange in the middle.
And then
milk into the orange, and then the orange into the milk. So to be clear, to do this cleanly at least, we do need temporary storage. We need an additional 8 or 32 bits, whatever it is, or in this case a cup, to actually be temporary storage. But at the end of the day, does the algorithm Maria proposed work correctly? OK, so let's try. Go ahead and do it and just restate for the group what you're doing. Orange is going into the middle. Orange going into the middle. Nice.
And the milk is going into
Milk is going into where the orange was. And the orange is going into where the milk was. So a big round of applause for Maria for swapping 2 cups. Thank you. So unfortunately, remember the bit of code that kind of corresponded to this idea the other day. Here's a function called swap. It has no return value because it's just supposed to do something. It doesn't need to hand me something back. It just, like Maria, is supposed to swap 2 variables. And it looks pretty correct. I mean, it's certainly arcane. It's C code. It's not sort of very reasonable human speak. But it's saying, give me an int and call it A. Give me another int and call it B. And then it's saying, like Maria did, give me an empty cup, calling it temp. Put A into temp. Put B into A. And then put temp into B. So at this point in the story, so to speak, this algorithm and this code is arguably correct. But let's see what actually happens here. Let me go ahead and recall that it wasn't quite correct. And we introduced a tool on Tuesday night called GDB, for GNU Debugger. And a debugger is a program that helps you, the human, remove bugs from a program, really by helping you poke around the insides of a program and understand your program better. And I can't emphasize enough, if you take nothing else away from tonight, is that debuggers are your friend. And even though this week, next week, the next few weeks, you will absolutely feel it's not worth the learning curve of fighting with some stupid arcane command line interface GDB just to poke around a program. It's a lot easier just to like another printf, compile, run, another printf, compile, run. That will not work in the long run. And so this is one of those things where spend the extra hour or two now, and it will save you tens of hours over the course of the future. So with that said, let's go ahead into my appliance here. Let me close the files that we had opened. Let me go ahead and open up a file called, in my source for Wednesday directory. Actually, let me get it from my downloads. Source for Monday, noswap.c, called noswap just to make super clear that this is intentionally buggy. So let me go ahead and run this. I'm going to go into that same folder. I'm going to zoom in so we can see it more clearly. Make noswap, enter. Seemed to run OK. And now let me clear the screen here. Let me give ourselves a little bit more room so that we can see the results here. Zooming in. And now this program, actually, let's look at the source code real fast, just to recap. Recall that this program, super simple, main function, give me an x value 1, give me a y value 2. Then let me say x is 1 and y is 2. And then the only interesting line really is down here. After I say swapping, I actually call swap. And I pass in x, I pass in y. And you'd like to think, like Maria, they would swap x and y. And then just to prove as much to myself, I'm going to claim swapped and print out x again and print out y again. So all of this is just sort of uninteresting printf, except for that line calling swap. So swap is exactly as we saw a moment ago and on Tuesday. But let's now use GDB to confirm or deny that the code is correct, and that it really does mimic what Maria was doing. So let me go down here, and let's first run it and see what comes back. So no swap, enter. That does not look swapped. Right, and that's kind of where we left off last time. It does not seem to work, and yet, damn, that code looks correct. So let's do this. Let me instead run GDB, and then run no swap. Whoops. No swap. OK, and now I'm at a GDB prompt. So it looks like a blinking prompt, and it is, but it's no longer my command prompt, my shell. This is now inside of a text-based program called GDB, the debugger. Let me go ahead and type run. Notice it says exactly what it's running. And this was not all that helpful. I've essentially run inside of a debugger the program again, seeing the same output. But what's cool about a debugger, recall, is that I can set breakpoints. I can tell the debugger, let me poke around at this part of the file by literally typing break. And I can do a specific line number, like 1 or 10 or anything. Or I can even say function name. So break in main. And let's do that. So enter. breakpoint. And here's a nice example of hexadecimal. And this is another reason we introduce it, not just for file I/O. Turns out that human programmer convention is to also talk about memory addresses in RAM using hexadecimal. Because, right, God forbid we used binary. It would just be atrocious to say or read. This is a little more compact and a little more conventional than decimal. So now let's go ahead and step through this program. I've set a breakpoint. And so now I'm going to go ahead and say run again. Let me zoom in. Run again. And now notice I'm at line 16. Let me scroll up for a moment and give context. In line 16, we're pretty much at the top of the program. But what the debugger has done is it's paused execution, so that line of code is not yet executed. So if I type print x, it's not printf. Inside of GDB, you literally say print. What would you expect to see if I do print x if my claim at the moment is that line 16 has not yet executed because we've paused execution right before it? Junk? Sorry? Does not exist? Random value? OK, so let's see. In fact, any of you could be correct because we don't really know what to expect when you run it. In fact, we got lucky this time. It's 0, but that's not going to be guaranteed. In fact, let's see what happens next. So now let me literally type next. And recall that what next does is it executes literally next line of my program. And this is why I say the interface does kind of suck. Like, it's hard to kind of keep track of where you are in the program. But I would just propose doing it very carefully and deliberately. And just remember that what you're seeing on the screen is what's about to execute after. So now if I type print x again, what should I see this time definitively? Hopefully 1. OK, that part of the program is obviously correct. What about y? Probably junk, unknown, so junk. And indeed, we finally got one of these so-called garbage values. That's just because the RAM's being used for other stuff. There's some pattern of bits there, but I haven't initialized it, so it's some garbage value. So the $sign is just a GDB feature so that as your programs get more complex, if you want to refer back to some previous line that you previously printed, you can say like print $2 to print that earlier value. It's a way just to jump around in your mind. Good question. So now let's do next. OK, and now if I do print y, I should hopefully see 2, because my line of code, y gets 2, hopefully executed. OK, this is like week 1 stuff in C, right? There's really no magic here yet other than the introduction of the debugger. So let's step through, not by typing next, but just n. You can typically type the first character or 2, and that's sufficient. So next, next. But this is interesting. I want to see what's going on inside of swap. So I'm literally going to type step instead of next, because next would run it, but step over it. Typing step steps into the function so we can continue the story. So now I seem to be at line 33, which let's scroll up for just a moment. Line 33 is smack dab in the middle of the swap function. So with Maria, we were pretty sure her algorithm was correct. I'm pretty sure the code mirrors what she said, albeit more technically. So now let's see. What should be inside of temp at this point in the story? Junk, hopefully, right? Because temp has not, that line, 33, is not yet executed. That's a real garbage value. It's negative in this case. So if I print a, though, what should it be? It should be 1. Because remember, let's go back to the source code for just a moment. The arguments or parameters for swap are called a and b. But we could call them anything we want. But the original values are called x and y. That's totally fine. But apparently x is becoming a and y is becoming b. So that's why if I do print a, I should hopefully see x's value, which is indeed 1. And if I print b, 2. So now, just to confirm, temp is still garbage. But if I type next, nothing seems to happen yet. But now if I type temp, what should temp be? If you scroll back to line 33, which is still on the screen. Should be 1. A should be 1, temp should be 1, and b should still be 2. Phew. So we're in the right track. We've swapped one of the beverages. So now if I do next again, now a has the value of b. So print a should show me 2. Good. And just to recap, print a is 2, printing b is 2, and hopefully printing temp gives me 1. Otherwise, I've lost the value altogether. And that's why we had the third cup. OK, good. We still have all the information we need. Let's do next once more, where b is going to get temp per line 55, or 35, which is still on the screen. So now I'm at the curly brace, which hasn't closed yet. So now print b, and it hopefully is 1. Now temp is still 2. What? Why does temp have 1? Well, think back to the code. Let's go back to the code. We only assigned temp a value once. Temp was assigned the value of a, which initially was 1. So what appears to be happening, it's good that we sort of had a disagreement there. Think of each of these variables as truly being distinct chunks of memory in the computer. In fact, for just a moment, if this, for the sake of discussion, is x, and it had the value 1, and this here is the value of y, and it had the value 2, what appears to be happening so far is that when I have another variable inside of swap called a, this is taking on the same value, but it's not the same box. It's not the same chunk of memory. It's another chunk of equal size, and b is taking on this value. Meanwhile, temp, which is another chunk of memory somewhere in the computer, is initially being assigned the value 1. Even when we put b in a, this does become 2, but they're different chunks of memory. So there's this independence. And this is why C is kind of nice. It absolutely takes some getting used to because it's so low level, but there's no magic. Like the computer is literally only doing what you tell it to do. But unfortunately, the end of this story, when we finally put temp into B, is that per GDB's confirmation a moment ago, this is the state of our world right now. And I think we were unsure for a moment, but temp, agreed, is still 1 because it's a different chunk of memory. It's only been saved 2 once. So what happens the moment the swap function returns? Temp gets pulled out of the memory. So temp disappears. We lose access to it. It goes out of scope, to use terminology from weeks 1 and 2. But what happened to x and y? They stay the same because they're different chunks of memory. So the metaphor here with Maria doing the cup swapping isn't quite accurate because, well, actually, it sort of is if we think of these as also cups. They're just the original containers, and we didn't use all of their values here. They were unchanged, right? This is still the original orange juice container. There's still orange juice in it. Milk has milk. So you can think of this really as an x and y. And Maria successfully swapped a and b, but she had no effect fundamentally on x and y. And again, it's a bit of an imperfect comparison because these are distinct chunks of memory, and I just used half the milk, half the orange juice here. But that's fundamentally the issue. So code correct until it actually returns, and then all of that hard work that we did or Maria did is sort of lost. And in fact, we'll come back to this, but if I draw this picture a little more technically, you may recall this picture here where we said there was something called the stack down here, and I alluded to something called the heap, which we'll get back to before long. Essentially, when you call main, main might get this chunk of memory here. When you call swap, swap might get this memory here. But as soon as swap returns, as this gentleman was proposing, that sort of goes away. The values are still there, but they've had no effect on the original memory main. So this is really bad, right? We could seem to have powers in the real world that we don't have in the computer world, even though these things are supposed to be at least as good as humans as doing tasks like this, moving things around, copying values, and so forth. So how can we actually go about fixing this? Well, let's identify the problem a little more precisely with this example. Let me go ahead and I'm just going to quit GDB. That program is broken. Right? Like it's going to require a bit of tinkering to fix it. So let's instead go into another example here, also available online for later reference, called compare 0, and see if we can't really tease apart in advance or predict in advance what's going to happen here. So let's propose that this program does the following. Main function here, get a line of text, store it in a variable called s. So again, no magic yet, sort of week 1 C stuff. And now get another line of text, but call this string t. So suppose I type in these values. What exactly is going on in the screen? And we'll actually see some similarities with these pictures as we saw a moment ago. So if I have declared s, and frankly, as you write code or sort of wrestle with some of these topics for the first time, absolutely start writing things down. If I declare a string called s, let's start drawing it as a square, 32 bits, what it will represent. Let's call this s here. And now getString. All this time, what has getString been doing if I do this? Let me go into this program, do make compare 0. Oops, let me go into the right directory. So make compare 0, / compare 0, enter, and let me type something like sorry and David. Okay, they're obviously different. This program compares strings and says different or same. So that's pretty good. So that was correct. Program seems correct so far. Let's do it again with Sadi's name. And you know what? Let's do it with his name again. Damn it. So not so correct. Well, maybe it was just, a fluke. Let's do it again. Okay, no. I mean, this is the thing about computers too. Maybe it's the lowercase issue. No, still different, but what is going on? So let's really think about what's going on and how C is really letting us do these low-level things. So here's S, and it's got something in it. I don't quite know just yet, but thus far, we've probably been thinking about S as storing a string. So inside of S is a string. So it's like cramming in Sadi's name here like this. But we know already that there's like a \0 somewhere in there. So this isn't quite legitimate to say. So let's draw what's really happening, which is that there's this string here, which has S-A-R-I, and indeed that \0. Each of these slots is a char, or a character. But if this is what getString is doing, it's getting my keystrokes from me being the human, typing in his name, putting it in memory somewhere, then what the heck is going in S? Because like just visually, it's not going to fit in there, especially since I already claimed that it's only 32 bits. And this is 1, 2, 3, 4 bytes, so it's at least 40 bits, because it's actually 5 bytes here, not even just 4. So how do I fit this in there? Put an address. Yeah, so it turns out, and what we would typically do is say, you know what S really is? It is a so-called pointer that looks like this. But let's be more technical, because like, what is this? How do you draw an arrow in a computer? Well, realize that when I type in someone's name, like Sadi's here, you can think of each of these characters being somewhere in RAM, in the computer's memory. And that RAM, if you've got 2 gigabytes, that means you have, what, 2 billion bytes of RAM. So let's just arbitrarily number them. This is byte 0, 1, 2, 3, 4, ... 2 billion. So let's on the screen do this. This is byte 1, 2, 3, 4, 5, 6 would be here, and so forth. And just to be a little conventional now, I'm going to prefix this with OX, 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 just because hexadecimal, again, is what we use when talking about addresses. But it added no interesting information there, just a convention. So what then, to be clear, might be stored in S, this box? An address. OK, and which one? We seem to have a few at our disposal, even though it's a little hard to read my writing. Let's go with OX01, the first byte. So when all this time you've been calling getString, it is getting a string, and it's putting it somewhere in RAM, but it's returning a value. And the equal sign to the left of it is assigning that value somewhere, to S in this case. So what does that really mean? It turns out that even for something as fancy as a string, which is a whole bunch of characters, might be 4 characters, might be 4,000 characters, it suffices just to remember the first byte in a string. For what key reason? Why is just remembering one number and not 4 numbers or 5 numbers sufficient? Say again? Where the memory location starts. It's where the memory location starts, but how do I know where Sadi's name ends? The \0. And that's why that thing has been so important. Because with C, you can represent a string just by knowing that there's this little box inside of which is the address of the first byte. And yes, you're not storing the last byte, which might be helpful, but you can always find it. Unfortunately, how long does it take to find the length of a string? How many steps to find the length of this string if you only know where to start? The number of chars. So it's a big O of 1, it's big O of n operation. It's a linear time algorithm to find the length of a string, because if you only have this little breadcrumb, which means, OK, look here at OX1, and now count, like, is this \0? Is this \0? Is this \? This is a linear algorithm. So big O of n, here's \0. And if I do as you propose, just count up the characters, OK, it's of string length 4. And that function, if you've used it, strlang, does exactly that. It's like a for loop, or it's a while loop, whatever. It doesn't really matter, but it is a linear time algorithm, because C simply represents things like this. Now, as interesting as this might be to real geeks, this is not all that enlightening sort of for conversation's sake, for designing algorithms. Like, who the hell cares where the memory is? And so we do very reasonably just start drawing arrows. It's a pointer to a chunk of memory, because the particular location really doesn't matter. But let's see then an example of, let's see why this is the case and where this ultimately is going to lead us. So compare 0 is broken, but what is compare 0 doing? Beyond getting S and T, notice how I implemented it a moment ago. If S equals T, I print out, you type the same thing. But we never saw that answer, even though I typed Sadi multiple times correctly. But we did see you type different things multiple times. So why are S and T apparently never the same, even if I type in SARI enter again and again and again to this program? Perfectly the same. Let's someone else. Yeah, and back. They're at different addresses. S does get a pointer to the address of SARI that might be over here. And T also gets that, but it's just some nice human coincidence that they're the same. C and computers in general are pretty low level. Even though it might look identical, it's not going to infer that for you unless you tell the computer to know that they're identical. So really, if I type his name twice, I'm going to get an identical looking chunk of memory, but that's fundamentally elsewhere. And if we number them here, maybe this is somewhere else in RAM. Maybe this is like OX100, OX101. And I'm kind of misspeaking since it's hexadecimal here, but it's somewhere else. And so that means a different value than OX1 is going to go here. It might be OX100 in this case. All right, so how do we fix this then? How do you compare two strings? Surely we can solve this. Sorry again? At the addresses. So you really, if I want to compare S and T, it's clearly not sufficient just to say is S equal to T, because OX1 is not equal to OX100. So that much seems to be true. So what can I do instead? What if I compare the first characters and then like plus plus? Compare these, plus plus, plus plus. I'm at the end of the string. If I haven't found any inconsistencies, return true. The strings are the same. So in fact, a pre-made program I have here, compare1, does exactly that. I'm going to scroll down to the interesting part, and I'm kind of punting to a library function, a function that the authors of C gives us. Stir comp for short, takes in two arguments, string, comma, string. And a little confusingly, it returns 0 if they're the same. Else it returns something else, meaning they're different. And in fact, it returns something else that's helpful. It returns a value that's less than 0 if alphabetically one string should come before the other. And it returns a value greater than 0, a positive number, if the reverse is true. So you can actually use this built-in function for sorting, because it will tell you not just equal or unequal. It will tell you does one come before or after the other string based on their ASCII values, which think back to week 1 as well. Now there's one other implication. Let me show one other example of this problem, but there is in fact a solution that we'll now see. So this is a program called copy0, and let's take a quick look at what it does. It first grabs a string and calls it S and gets it from the user. And then why am I doing this? I won't dwell too much on the error checking, but when might getString return null? Why do I bother checking? Say again? If there's no input and technically it won't, if there's no input, if the user just walks away, the program will. Yeah, so really if the computer runs out of memory is the more common thing, or if the human types in such a long string that it can't fit in memory, getString would return null in that case as well. And null, as an aside, and there's a reason that I didn't use 0 on the screen, null is a special value that humans have decided nothing can go at. OX0, or just 0, is the null address. And just by convention, we make sure that we never put real data at OX0. And this is why a program, if you accidentally try to touch something that's null, or use it in math, or use it in printing, your program will typically crash, because you're trying to access memory that is not yours by definition. So this is just some error checking to make sure I didn't screw up. And now down here, what am I doing when I try to copy the string in this way? I claim that this program is copying a string. So if I type in Saudi, and I've declared both S as a string, and I've declared T as a string, what happens when I do T equals S in terms of my picture on the screen? If the goal, again, is ideally to copy his name. I'm only copying the address. So that means really, if OX1 is up here, then OX1 ends up here. Or pictorially, it's as though T is also pointing up there. However, this program is called copy. Would you claim this is would you say this is a copy of S? No, and in fact, what's flawed about this program, and let me do this here, I'm going to go ahead and make copy0. And now let me run copy0. Let me go ahead and say something. Sorry, in lowercase. This program capitalizes things. And if we look through the source code, that's what it does. It's supposed to only be capitalizing the copy. Why is that? Well, let me scroll up to the code again. I've copied S and T, but that's what's actually happened. And now scroll down to line 31 onward. I'm using our old friend 2upper, which may be used for Caesar, Visionaire, or something. Actually, probably not for those, but you might recall that 2upper just returns the uppercase version of a letter. But notice what I'm doing. I am changing the 0th character of T to be the uppercase version of the 0th character of T. But according to this picture, that is the same as doing what? changing the first character of S, because they're literally one and the same. And so this program, in theory, per my printf, is supposed to be just capitalizing the copy. But if I type Sadi's name in lowercase, I see that both the original and the copy, per these lines of code, where the first prints out S and the second prints out T, are both printing the same darn thing. So what fundamentally, putting the so-called engineering hat on, especially if you have no technical confidence of what the right answer is here, just like conceptually, how do we fix this problem? Even if you don't quite have the functions or the vocabulary just yet. We need to put the copy at a different address. So we kind of need to magically give me another chunk of memory. And indeed, getString effectively is doing that for us. It's always getting us another chunk of memory. But getString doesn't copy strings. It gets new ones. But we need a function that somehow gives me a chunk of a clean slate, a chunk of memory here, so that then I can copy the string by doing something quite like stir length. I just kind of put the S and the A and the R and the I and the \0 down here. And we indeed have a technique for that. And indeed, whereas everything we've been doing thus far, for the most part explicitly, steals memory from the so-called stack, now there's this sort of repository up here called the heap. It's just another portion of RAM in a computer that if you want to allocate memory that sticks around even after functions are called and returned and kind of come and go, you just want it to be around, you can use a chunk of memory called the heap. And all this time, that's what getString has been doing. And we fix this in copy 1. So I'm going to scroll past the comments and stuff up top. This is the cryptic line that will solve all of our problems today. Malloc, for memory allocate, so give me memory, is working as follows. Well, it turns out all this time, the thing we've been claiming is string, string, is just a synonym in the CS50 library for something more technically called char star. It turns out that the star operator means give me a variable that is not a char, but is that the address of a char. So give me a box that looks like this, but don't put a char in it. Put the address of a char in it, a number, if you will, that starts with 0x. So malloc, memory allocate, and this is the complex looking formula on the side, but it's actually pretty straightforward. One, if I want to create enough space so that this box is as big as this box, what math do I have to do? I want to get the length of S, so that's Sari, S-A-R-I, that gives me 4. I then apparently want to add 1 to it, y plus 1. Yeah, I need space for the \0, so I need the 5th byte. And then just to be super careful, I'm going to say times that by the size of a character. In reality, a char is going to be how many bytes? 1. So I could reasonably just say times 1, but even that's kind of stupid. I can just get rid of that altogether. But I'm just being super proper to make super clear how many bytes of memory I want. So based only on this, and it's a little cryptic syntax at first glance, memory malloc must be returning what exactly? It's giving me a chunk of memory, and what is it handing me back? An address of memory. Specifically, if this is a whole bunch of bytes of memory, right? It's a big chunk, but really it's a chunk of bytes. Which address is it handing me? Not random would be bad, but good thought. The beginning. The beginning is what's key. And I say random would be bad, or rather, it's choosing the chunk of memory, presumably from some random location in the computer. And it's not quite random. It actually manages it pretty efficiently. But once it's decided, here are your 5 bytes, 1, 2, 3, 4, 5 bytes, it then is going to return to me, given that it's a function that has a return value, it's going to give me the address of like 0x, and we'll call it 100 again arbitrarily. It's going to give me 0x100, so that what really goes in T is the address of that new chunk of memory. So it's quite like getString. In fact, that function getString we've been using for weeks just uses malloc underneath the hood. And when the human types in characters, we just copy those characters into the chunk of memory that malloc gave us. So what's in all of these bytes when we first call malloc, do you think? I've just said give me 5 bytes based on that math. What's inside of those bytes? Random. I mean, so that part is random. It's just garbage values because it's coming from who knows where. It might have been used already previously. It's mine to keep now. It's coming from the heap. It's not going to disappear even if this function returns. And that's what's key. And we'll see more of this over time. But it's garbage until I do the copying myself. And that's where copy 1 finishes things up. This is just a loop here. It's a for loop iterating over the length of the string. And it's copying s bracket I into T bracket I. So put an S here, A here, R here, I here, and finally the \0. And now 1, if that weren't enough sort of new cryptic syntax, let me just hammer it home all the more and make it look lovely in retrospect. This is the last example here, copy 2, before we'll make everything happier with some claymation. Notice what I'm doing down here instead. This program, copy 2, is identical to copy 1, what we just saw. But notice this craziness. Whereas a moment ago I had this. T bracket I gets S bracket I, which frankly looks nice and friendly. It looks like week 2 again. Caesar and Vigenère, that kind of stuff. I claim that the line that I've highlighted here can actually be replaced, all the more confusingly, with this line here. But why do I propose this? So what's nice about C, even though it takes a while to wrap your mind around it, it literally is just doing what you tell it to do. And so the star operator has one more feature to it. When you use the star next to a word like char or int or float or double, even though we've only used it in the context of char so far, it means give me a variable that will store the address of that data type. But when you use it in isolation like this, with no keyword to the left, there's no mention of char on that line right now. There's no mention of int or float or anything. It's just a star at the beginning of the line. The star operator is also known more fancily as the dereference operator, which you can think more casually as meaning if you have an address, go there. It's like looking at a map for the address of this building and going there. Star means go there. So what does this mean? Well, here's my loop, starting at 0, iterating to the length of the string. So to recap, this is the loop that's copying SARI into the new chunk of memory, step by step by step. So on the first iteration of this loop, old school stuff, what's the value of I initially? Just to be clear. It's just 0. So on the left-hand side here, what's T plus I? It's going to be the same thing as T, right? Because it's T plus 0. That's a no operation, so it's just T. So star T means what? Go to that address. So what's the address at the moment? I've been saying arbitrarily it's like OX100 or something. So star T means go there, like literally with your finger. Now sorry, wrong place. So if I'm saying go to OX100, go there, which is the chunk of memory, the first byte of the chunk of memory. So now on the right-hand side, it's pretty simple too. What's S plus I when I equals 0? It's just S, right? Because that has no effect. So that means go here. And what I'm saying with the equal sign, as always, is copy this S's contents into T's. Now what's really sexy about this loop is now on the next iteration, what's I the second time around? It's not 0, it's 1. So T plus I is T plus 1. So that means mathematically, here's the address OX100. T plus 1 is going to be OX101. And S is going to be like OX1 plus 1, which is OX2. So that means copy the A into here, and the R into here, the I into here, the 0, \0 into here as well. So this is a technique known as pointer arithmetic, which means exactly that. Your pointers are addresses, and you're just doing arithmetic on them. And now, admittedly, only if you want to kind of show off would you generally write your code to look like this, because frankly, it takes most anyone sort of a moment to think about what's going on, and that's not necessarily the best use of the programmer's time. So it's completely reasonable to do what I did the first time, which is much more intuitive, and again, much more weak 2 friendly, which is the so-called syntactic sugar. Just a fancy way of saying just simpler notation. But that's all the compiler Clang is doing. When it sees you typing something like a variable name, bracket, something, bracket, it is converting it underneath the hood to some super simple arithmetic, much like the sexier but if more complex version. Yeah?
Should we eventually graduate to using code like that, or is it okay to just stick with that even after a while?
Really good question. Should you stick with code like this, or should you graduate to the pointer arithmetic? Really, it's completely up to your comfort level. I would argue this is much more readable. And if I'm working with a partner or if I'm submitting code for other people to read, I'm probably going to go with this because it's just so much simpler to look at. But if you end up doing more complicated functionality, sometimes it might make sense to make the math explicit when it's not just individual bytes, but maybe it's a student structure or something a little more complex where you want to be more deliberate. But the shorter answer is totally depends. One is no better than the other. This is truly in the language as syntactic sugar, which means it's just a nice user-friendly syntax. And we'll see a couple other incarnations of such syntactic sugar. So let's look at one last piece of code, and then a friend of ours from Stanford University, by way of some claymation on video, will actually tell us what it's all about. So here we have an example of code involving pointers. And let's consider for a moment in English what this program is doing. Main is the name of the function. I've got 2 lines of code up top. And in the simplest but still technical jargon you can, what is this first line doing? How would you describe this to a somewhat technical person?
It's reserving a space in memory for x.
OK, it's reserving space in memory for x, but let's be a little more proper. Someone want to expound on that? Careful, it's not going to it because the star means go there, only in the absence of a type to the left of it. Getting it? Well, be more specific. It's giving me a chunk of memory that what? Oh, wait, one sec. Almost. It's allocating a chunk of memory for an address of an integer. So that's what's different. Prior to an hour ago, int x, semicolon, would mean allocate a chunk of memory for an int. The story is changing ever so slightly now to say allocate memory for the address of an int. So you can still use both techniques, but when you want an address, you say this. So similarly, give me a chunk of memory for the address of an int and call this one y. So at this point in the story, we have 2 chunks of memory, not unlike earlier. One is called x. One is called y. I don't know what's inside of them because I haven't assigned them any values, so they have garbage. What is this doing, though? Malloc size of an int. How many bytes is this giving me? Size of an int, which is 32 bits or, not quite, 32 bits or 4 bytes. So what this is doing, when I call malloc, it means give me enough memory for an int. So this too, I'll draw it as a square as I keep doing for 4-byte values. And I'm going to call this, actually I'm not going to call it anything, but this has an address. Let's call it arbitrarily OX50. That's where it happens to be inside of my Mac or PC. So what gets stored in X according to that third line? What do I put or draw in X? 0x50, right? Because if I'm saying malloc, give me a chunk of memory, that's giving me this chunk of memory. And I'm saying x equals it. So I'm putting the address of that chunk of memory in X. But again, who really cares where these things are? What's a cleaner way to draw this now? And just a pointer, like an arrow to that chunk of memory. Same thing. And now what else is happening? So star x gets 42, so-called meaning of life. So star x. What does star x translate to casually? Go to x, or go to the address in X. So what does that mean? If you've ever played the game like Chutes and Ladders, where you kind of like go like all around the board, so go to the address in X, which is here. So kind of follow that chute. And now what do I do here? Yeah, this was a question mark, garbage value, but now it's obviously 42. Nice. So now next, almost there, star y gets 13. So what does that mean? But I can't create I can only create boxes when I allocate memory or declare a variable. I want to go to the address in Y. What's the address in Y? No, never. Nothing happens in C automatically unless you tell the computer to do it, yeah? Oh, you wish it would dynamically allocate it. No, the computer in C is only going to do what you tell it to do, yeah? I'm forcing it to go to the address 13, not even. Again, let's rewind in the story. When I said star x gets 42, that means go to X and then go to the address in it, so go there. So where do you want me to go if I'm currently starting at Y? How do I go to this question mark? Where is the question mark? Right? Like there is no answer here. Like going to a garbage value leads to undetermined behavior. Your computer will crash or freeze or the program will quit. Like bad things, to the extent that was bad, happen. Much like the following film. So a dear friend of ours at Stanford University, Professor Nick Parlanti, spent a lot of time, as best I can tell, in like his basement making claymation a few years back to depict exactly this story using a character called Binky to represent precisely the story we just told on the board. Let's end here with Binky.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So, are we gonna switch places now? Oh, look, we're out of time. But just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
Time for discussion and Q&A in just a moment, but it has been so much fun and such an honor to be here. This is CS50, and this, to bring us home here, is Colton Ogden.
Okay, I know you're mad at me by now. Sorry about that. Hope you forgive me, guys. Would you forgive me? Okay, now I feel better. All right, I want to go back to our first lecture. Remember, I told you we want to give you the best experience in computer science as introduction. So we decided to take the best course in computer science and from one of the best schools in the world and bring it to you. However, this is going to be a challenging course, but we're going to do our best to make it as close as world-class education that's given in Harvard. Therefore, we give you the assistance that it takes. And I told you, we can't bring Harvard to you. Therefore, we're going to bring those videos every single time, and we're going to build on them. But guess what? We actually got Harvard. They were very generous to come down. So please, we are doing our best. And as I asked from you at the beginning, we only want you to give it your best shot. And it's going to be working great. Okay? So please keep going. Put the effort as you were doing. And let's make it till the end. Thank you for everything.
Davin in back would like to join us, and certainly any of the MDC TFs. We thought we'd take any questions that you might have, and then we'll save some time to mingle about and chat more casually. Here we are. Enhance. Sure, wherever you're comfortable. Yeah, question.
This is a question for
Davin.
Yeah. No, not Davin. I'm sorry.
Oh, sorry. Do you have the microphone still?
Yeah.
Okay.
Did you pre-program those sounds? Did they come already programmed with that voice?
So the first song I played was by a guy named Nev, Louder, which is a mashup of. I can start over. The first song is this going through?
Sure, of course. Yeah.
You can't hear it. Oh, it is?
It's recording.
Okay. So the first song I played was called Louder by Dr. P and Flux Pavilion. It's a mashup that was created by a YouTuber named Nev. And this was his project file. So basically, I'm just covering it. And the second one is by M4 Sonic. And that one is called Weapon. And that's also by him as well. And they're all basically, each of these buttons on this controller, in a program called Ableton Live, you can tell it. Yes. So using Ableton, you basically create a drum rack, and then you put each sound that you want on each of these buttons. So like you can tell this one just to play a sample, and you can just play basically whatever you want. You can configure it in different ways, and then make the lights go and do their thing. But to answer your question, I didn't do it myself, but that's how it works. So.
Second question.
Yes, I mean I love Ableton. It's very user friendly, but I mean FL Studio, Pro Tools, they all pretty much do the same. For a beginner, I would recommend Ableton, but even like Apple's Logic is really good. Really good for beginners. Good learning curve. No problem.
Sure. Here.
Sorry, say what?
Oh no, we are here entirely for Miami Dade College.
Would have been fun.
Back.
You were talking about not being able to enhance images earlier. With JPEG, you just replace vector images, all that.
Good question. Some file formats have vectors underneath them, EPS, for instance, TIFF, and depending on how you save the files. And in those cases, yes, if you have a vector image file, which means you use mathematical formula and not dots to represent it, those can scale and contract infinitely without loss of fidelity. So that is the salvation there. Good question. Other questions? Yeah? Oh, good question. So the answer is kind of the same, to be honest. So if you think about how you represent an image, you could certainly think of it as a grid of width and height. And there's a whole bunch of dots in rows and columns, and each of those rows and each of those dots is represented with a pixel. Maybe in the simplest form, it's a 1 if it's a white pixel, or a 0 if it's a black pixel. That would be a black and white image. Or use 24 bits if you want to have millions of possible colors. But to this gentleman's point, you could absolutely take all of those zeros and ones and come up with some mathematical formula that represents that very same image that may or may not take more space depending on the complexity of it. But generally, vector files tend to be more efficient because using fairly concise mathematical formulas, you can then blow the image up to be as big as you might want it. So short answer, yes, for a very similar reason. Other question? Ableton question over here.
This is for anyone, but I'm pretty sure he's an answer again. Have you mixed music and coding in any way?
Mixed music and coding. So Ableton Live, I guess something called digital signal processing, DSP, is basically the mathematical representation of sound and how code basically represents that and how you can manipulate it. And that's sort of the underlying way that which you would code something like Ableton or like a synthesizer. I encourage you to maybe look up DSP and how it works more low level. But mixing, was there anything more specific that you were referring to in terms of mixing music and coding, or? I mean, I've dabbled. There's like some JavaScript libraries that kind of let you model sound in a little more high-level way than you would do in something like C++ or C, for example. But basically, it translates to emulating things like sine waves, square waves, sawtooth waves that are oscillating at a certain frequency. Yes. Not cosine waves, but sine waves, sawtooth waves, square waves. They're basically different waveforms that oscillate at different frequencies, and the different types of waves that they are correspond to how they sound. And it's basically manipulating those waves that you get sound, digital sound at least. It's actually, that's pretty much the building blocks for almost any sound. So. Yeah, question over here?
So, with the way that we learn to allocate memory, is that what we should be doing from now on?
It's a good question. Is that?
Just int x, int y?
Good question, Davin?
That's coming soon.
So, when you're allocating memory, where are you allocating it from? Sorry, when you're allocating memory, where are you allocating it from?
Enhance.
Enhance. You're going to be allocating it from the heap, right? So if you're allocating stuff on the heap that you want to stay around for a while, then you want to use malloc, because when you're mallocing or getting memory from the heap, it's not going to go away. So if I have a function, I'm mallocing memory, then when that function returns, I still have access to that memory. If I just have an int x in a certain stack frame in a certain function, and then I return from that function, am I going to still have access to that variable? No, right? Because when that stack frame pops off, then that variable basically goes away. Yeah, so whenever you want access to a variable past a function, you'll probably be using malloc, or whenever you want memory from the heap. No, because you can definitely change the value of x. So you can definitely change the value of memory you've malloced in the heap or the stack. Basically just, I don't know if you've really gotten into memory management yet, but you have two pools of memory. You have a stack and you have a heap. And you kind of think of a heap as this general pool of memory that you can pull from. And this heap, that when you pull memory from this heap, you have a pointer to it, and you're going to be able to pass that pointer around, but you basically maintain that reference to that memory in the heap. So you're always going to have access to that. But if you're in the stack, for example, let's say I called a function, and then I set int x equal to 5 in that function, and then I return from that function, the function that called that function, sorry, it's getting a little complicated, isn't going to have access to int x, because when it pops off that stack frame, I'm not going to have access to that memory anymore. Whereas if let's say I malloc memory and then I return a pointer to that memory from that function, then the function that called that function, sorry, it would be better if I was drawing it, but would then have access to the memory I malloced. So.
Okay.
TLDR.
No, unless using malloc will solve an actual problem for you, as in the case of swap for us today.
Yes. Nailed it.
What inspired you open CS50 to the public, to like EDS?
It's a good question. What inspired us to open the course to the public? For me, it goes back a while. Back in 2005, 2006, I was teaching a course at Harvard's continuing education program for local adults, and this was when podcasting, the word, had come into vogue, and all that meant was posting MP3s or audio files online of courses. And we did this at the time only so that our own registered students in the class could literally, go on a treadmill and listen to a lecture, or be on the subway or the train or whatnot, and generally avail themselves of the course's material in a more convenient way. And then it sort of gained traction, and we were astonished back in 2005, 2006 that other people in the world actually cared to tune in. And so when I inherited the reins of this class, CS50, in 2007, we immediately put the course online. And I've very much philosophically become a fan of what's called open courseware, just putting materials out there because it's the right thing to do, I think. And if others can benefit from it, all the better. In fact, the feedback loop, too, has been wonderful. And we've been getting to know Launch Code more recently, both in St. Louis and now here in Miami. And it's been really heartwarming, honestly. Like, this actually really means a lot to us to be here and to see a group of people, of all things, taking an interest in a computer science course we produce in Cambridge, Massachusetts. It's just really cool and really exciting. And I think I all of us are just really exciting to see where this might lead. Sure. Question there.
I can't compile my code.
Unexpected end of input. Sometimes this is your fault, sometimes this is our fault, since Check 50 has its own bugs. It's hard to say without seeing the code, to be honest. So if you okay, well, so says many a student. How about this as sort of quid pro quo here? Email me directly your code, and I'll take a look and see if we can't chase the issue down. Check out my email addresses in the video. Yeah. Oh, sure.
And my, question is, why would you choose the appliance environment instead of an IDE?
Why would we choose the appliance instead of an IDE? It's funny you should say. So short of it is, one, we wanted to use a Linux environment, and we've looked at things like Eclipse is a popular one, NetBeans is a popular one, Code Blocks, and there's many, many others, Visual Studio and the like. And all of those, for my pedagogical taste, are just too heavyweight. They've got too many menu options, too many buttons. There's too much magic clicking a button as opposed to typing a command. And so for us in CS50, I've pedagogically wanted us to get students as close to the computer as possible while still avoiding the headaches of certain of arcane interfaces. So gedit, I think, is a very nice compromise between a full-fledged IDE and a very black and white text editor, because it gives you syntax highlighting, it colorizes things for you and the like. I say it's funny you should say that now because we're considering this coming fall for the next version of CS50 and CS50X transitioning to a web-based IDE that will be more similar to what I suspect you have in your mind. But even then, it's still going to have a built-in terminal window. It's going to use what's called virtualization or virtual machine. So the student's experience will pretty much be the same. But instead of downloading a 2 GB file, you'll use a web-based version thereof. So we're getting to that, but it's motivated ultimately by pedagogical interest, not necessarily what's most popular. Yeah.
To create pointers and pointees and stuff with the heap. Once the whole entire main function completely shuts down, which is your program shuts down, those pointers still stay active within the heap?
Short answer, no. So what you get when you run a program, you get the illusion of full unfettered access to like the full 2 GB or more of your computer's memory through something called virtual memory. There's sort of a layer of indirection where the computer pretends like you have access to all the memory, but you don't actually. It sort of shares it among multiple programs. And the reality is when you quit a program, all of your memory is no longer your own. The zeros and ones might stay there. Your data might become someone else's garbage values, but the reality is that the data sort of automatically, the memory is automatically reclaimed for you. And we didn't see it tonight, but the opposite of malloc is a function you'll soon see called free, which hands memory back to the computer, which you should do to avoid something called memory leaks. And in problem set 5, which will challenge you with a dictionary of some 140,000 English words to implement your own spell checker and implement, using malloc and allocating memory from the heap for this reason, a dynamic data structure called a hash table or a tree or a trie. There too, you'll be responsible for allocating and deallocating or freeing the memory. Yeah?
So for example, if we have a value stored in the heap that could be
That's a really good question. If you have sensitive information, did you want to field or? Yeah, sure.
Is this working?
Yep, it won't amplify, but it will record.
Okay, so yes, when you have this information, when you open your program and you're allocating this memory and you save it, once you close your program, like David said, to answer the question, all your information is kind of set as free to allocate something else, and your values are garbage values. So if you have like a very nice algorithm to go through the entire memory of this computer, you might find that number or that information that you're looking for, but I would say it's way too complicated to get there, like forensics. I don't know if you can do it because you have worked with that, but I don't really know an algorithm that can get you to that point.
An adversary would typically get to it only if you have some bug in your code that lets him or her jump to an arbitrary memory address using something called often a buffer overflow exploit, which is coming up in just a week or two times in the video. But there are some operating systems. Mac OS has generally been good about this. If you poke around system preferences, if you have a Mac, and security, you can actually turn on something called secure virtual memory, which still works the same, but it encrypts the memory for you, so at least when your program dies, it just looks like random noise to a potential bad guy. Yeah? But the future of C? It's the past of C, really. Every few years, they do make some tweaks to the language. C99, 1999 was one year. 2011, I think, was the most recent update to C, but these are very marginal changes. What you're really seeing, honestly, is many, many new and exciting layers of languages on top of them. Python's very much in vogue these days, Ruby, and there's, hundreds of languages out there. So I wouldn't say so much that there's a future of C. In fact, CS50 does not teach C because most of you will ever again find it useful. And in fact, even today, I was worried I was going to embarrass myself because I haven't programmed C since like December of 2014. But it's testament to its utility for us as a teaching language, and the fact that so many higher level languages like PHP we'll use later in the class, JavaScript and the like, are so syntactically similar that you get a lot more functionality for free from other more modern languages. We shall see. We shall see. Send me an email. Now, a quick question. We use in the appliance Dropbox. Do many of you use it personally as well? So a whole bunch of you. OK, so our friends at Dropbox, and we'll adjourn in just a moment, and then all of us will mingle around, and happy to chat for as long as you'd like to stay. Some friends of ours at Dropbox gave us a slip of paper that has on it the URL to which you can go to redeem a coupon code, and that coupon code is good for 10 free gigabytes of Dropbox space in perpetuity. And what we did... What we did in advance is put this slip of paper under one lucky student's chair, if you'd like to look underneath your chair. So that's it for CS50. We'll stick around now for a while.